OK, so we're almost to the end here of control hazards. Let's talk about why an instruction may not be dispatched every cycle. Well, let's think about forwarding and full bypassing. This is sometimes really expensive to add. If you're trying to bypass out of every location in your pipe, that may be expensive. So we may still want to stall in certain cases. A good example of this is if you go look at a modern day, something like your Core i7 machine. They actually don't bypass between all the different functional units from all the different locations, because they can execute about 6 instructions per cycle, and they have many stages in the depth of their pipe, so they'd have to basically be bypassing out of 100 different places for every new source operand. So what you typically will do is you'll figure out what are the common bypasses that are needed, or the common forwarding paths that are needed, and you'll have those. And then some of the infrequently used ones, you just won't build. This will help with your cycle time, but hurt with your CPI. Loads can have, or typically have a 2-cycle latency. So we talked about this when we were talking about load to use. And the instruction after the load cannot necessarily use the result, definitely cannot use the result, because in our 5-stage MIPS pipeline, the result is not computed until the memory stage. So if you're in the execute stage, you would not have been able to get that even if you had bypassing out of the end of the load, end of the load pipe, or excuse me, end of the memory stage. And one interesting thing is that the MIPS 1 architecture actually defined load delay slots, very similar to what we have in what we had discussed with branch delay slots. So MIPS 1 had load delay slots, which were software visible slots that you had to fill and could solve basically this pipelining hazard. And the compiler would have to schedule some non-dependent instruction, so it was an instruction which was not dependent on the load, into that spot. This was ultimately removed out of the ISA, and stalling was put back in, because as you went to sort of different pipeline lengths and different microarchitectures, this started to be onerous. And this is really one of the big problems with both load delay slots and branch delay slots, is it's not very microarchitecture independent. So as you change to different microarchitectures, if you had, let's say, a pipeline length of 5 and it went to 4, all of a sudden maybe you didn't need that branch delay slot or something like that. And I wanted to sort of point out here is this idea here really is encapsulated in the name MIPS. It stands for microprocessor without interlocked pipeline stages. So they really did not want to have interlocking here on something like the load to use of that. And later in MIPS 2, that was removed and pipeline interlocks were reintroduced. So we could all find mistakes that we have done and have changed it. But in the original MIPS 1 ISA, they had load delay slots. Another good reason why CPI might be greater than 1 is we have conditional branches, which can cause bubbles. So this was all the control hazards we've been talking about up to this point. And you have to kill the instructions if you don't have some sort of delay slots. Now, I wanted to point out here when we talk about CPI, and this is this note at the bottom of the slide, is that you really want to think about CPI from the perspective of a usable CPI instead of how many instructions are executing. So if you are adding no-ops to your program and the no-ops are not doing anything useful, that should not go into your useful CPI calculation. Your machine might count that as valid instructions going down the pipe because it was software visible instructions, but that's not a good solution. When you should be computing CPI, you should always be thinking about useful CPI or CPI that's actually towards the end goal of the program. A couple other control hazards that we need to talk about in this course are other things that can change your control flow of your program. And those largely can fall into two different cases here. Exceptions and interrupts, and they're both related. And let's talk about what an exception is. So an exception is something where you have an instruction, and the instruction does some operation which is invalid or against what the intended use of the machine is. So a good example of this, there's a couple good examples, is you divide by 0. You take some value, divide it by 0. Well, on most computer architectures, this is ill-defined or undefined. So you'll actually get an exception, which is a divide by 0 error. And you could go try this out. If you go log into your computers and go write a little C program, take some number, divide it by 0, you're going to get a div by 0 error if you're running on Linux, and get something similar if you're running on Windows. And another good example of exceptions is things like a memory fault. You're trying to access memory you're not allowed to go access. There's some underflow and overflow exceptions in certain architectures if like number precision goes out of whack. If you have a floating point number which becomes too large or too small, and the floating point arithmetic can't handle the precision, you'll sometimes get underflow and overflow exceptions. And then interrupts are external things happening. And so something like a timer tick going off or an I/O device trying to wake up your processor or do something to your processor. And why these are important and why these are control hazards is these are unexpected things sort of coming into the instruction stream, and it's going to change the subsequent instructions that are executing. So there is really a control hazard. It's changing the program control flow. And we're going to be talking a lot more about exceptions and interrupts later in this course, but I just wanted to get this idea across in this review so far that exceptions and interrupts are different types of control flow hazards.